Algebra 2 Cram, New York State Algebra 2 Regents, Common Core, Basic Grasp of Inverse Trigonometric Functions. The range of the inverse cosine, sometimes called the arc cosine of x. Concept number 16. To order this complete Cram session, inbox me at memedicine@gmail.com. The odds of someone doing exactly what you tell them to do is pretty slim to none, but I guarantee that if you inbox me and order this complete Cram, you'll become an Algebra 2 master. Be sure to spread the word to your friends and classmates who also need to cram for Algebra 2. If this isn't the subject area you're looking for, no worries. Still inbox me at memedicine@gmail.com to order personalized packages. All right, so let's cram through the concept of the range of the inverse cosine, also called the arc cosine of x. Basic graphs of inverse trigonometric functions. Okay, so the range of the inverse cosine of x. Now, getting things in order is the secret to progress. So I want to give you a pre-example to organize your mind, okay? And in order to know what the inverse cosine is, we need to establish what the cosine is first. And basically, the way you get the inverse cosine is by switching the domain and range of cosine. So the domain of cosine function becomes the range of the inverse cosine function, and the range of the cosine function becomes the domain of the inverse cosine function. And remember that domain is a set of all independent or x values of a function where the function is defined, and range is a set of all dependent or y values where the function is defined. Okay? Now here you see we're referring to our angle as theta because we don't want to double up on variables. So actually this x actually represents a cosine or value. So it's not even an angle. So you kind of don't even need to worry about that. Scratch that. All right, so we have this angle theta and it's in standard position. It's positioned here in our x, y Cartesian coordinate plane. And the reason why it's in standard position is for the following factors. The vertex is at the origin at 0. The initial side ray is on the positive x-axis, and the terminal side ray terminates in quadrant 1, okay, at the extent of its y-coordinate, and the initial side ray goes to the extent of its x-coordinate. So we see the ray formed here, and the ray is actually a measurement. It's a magnitude. It's always going to be positive. But what we did was we resolved it into its x component, which can be positive in quadrants 1 and 4. Let's say this ray were located in quadrants 2 or 3. The x-coordinate would be negative. And we also resolved it into its y-coordinate, which is positive in quadrant 1. It also would be positive in quadrant 2 if the ray was located over here, but it would be negative in quadrants 3 and 4 if the ray was located in either one of these bottom quadrants, okay? All right. So what do we want to establish now? Yeah, okay. So inverse trigonometric functions are basically one-to-many functions. They're not one-to-one functions. When I say one-to-many, let's say you were doing the inverse cosine of 1, okay? This would return many values, many answers. Therefore, it can't be a legit function. A legit function has to be one-to-one, meaning it has to pass the vertical line test. And if you're like, what the heck is she talking about? Don't worry. I'm going to show you exactly what I mean in a moment, okay? And let me show you why this is. Remember I told you that this angle is in standard position. So whenever you input an inverse trigonometric problem into your graphing or scientific calculator, it's going to return a reference angle. And the angle comes from quadrant 1. It's acute. It's bound by the quadrantal angles 0 degrees and 90 degrees, okay? And let's say, for example's sake, this reference angle theta here is equivalent to 40 degrees. Oh yeah, we also need to note that we resolved our ray into a right triangle because of its x component and its y component, and that's why you see this triangular formation here. Okay. Oh yeah, and before I do the quadrantal reference angle demonstration, I also want you to note that the original function that precedes the inverse function is the cosine of the angle theta, or sometimes people like to call this angle x. Variable usage is arbitrary, but for the most part, people use theta or x. For the most part, x, okay? But again, we don't want to double up and confuse you. So this x is not the same as this x. I just put or because some people have never seen theta before. So the cosine of the angle theta is equivalent to its x-coordinate in the numerator, which I explained to you prior, can be positive or negative. That's why sometimes you get negative cosine values, divided by the magnitude of the terminal side ray or the hypotenuse, which is always going to be positive because it's a measure of magnitude, okay? So this is the original cosine function. But I'm going to show you what the inverse cosine function does. So let's say you want to undo the cosine function. You don't want to know the cosine, but rather you want to know the angle that generates the cosine. This is what would happen. So you would have to take the inverse cosine of the cosine value, which is x over r, and whatever you do to the left-hand side of the equation, you would also have to do to the right side. So let's distribute this inverse cosine function. And when we do that, we get the inverse cosine of the cosine value, which is x over r, or adjacent over hypotenuse, is going to be equivalent to the inverse cosine of the cosine of our angle theta. Okay? And you're going to see that these two cancel each other out and they unmask the theta. So the inverse cosine of x over r, or x whatever, some particular value is going to be equal to theta. All right, the angle. So any inverse trigonometric problem is going to yield an angle, and specifically it's going to yield a reference angle or principal angle that's located in quadrant 1. It's acute, okay? And I started to tell you that, let's say, for example, say theta is equivalent to 40. And let's say, I don't even know what the cosine of 40 is, but let's say you do the inverse cosine of blah, 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 and you get 40, okay? That's all your calculator is ever going to return to you. But that cosine value could correspond to an angle over here, or over here. I'm going to show you how to get that. And sometimes you're going to need to incorporate the fact that that same value can have a negative sign over here, but it would have a positive sign over here, okay? Or over here as well. So this can get a little bit tricky. So let's say we know for sure that we just want an acute angle in quadrant 1. We would accept our answer. But let's say we're not looking for the 40-degree answer in quadrant 1. We might be interested in the answer in quadrant 2. And what you would have to imagine in your mind is theta doing a vertical flip over into quadrant 2, and you're going to end up with something that looks like this. All right, so this is theta. And let's say you're interested in quadrant 2. What you're actually interested is not the theta, which is 40 degrees. You're interested in this big obtuse angle, okay? And in order to determine what the value of your angle of interest is here, you would have to subtract theta from the extent of quadrant 2. And the extent of quadrant 2 is 180 degrees. So 180 degrees minus our example theta leaves you with 140 degrees. So your angle of interest, if it were in quadrant 2, would be 140 degrees, which has the same numerical cosine value as 40 degrees. It's just that it's negative due to the fact that our x coordinate is in quadrant 2. All right, I know that's a lot to take in. Let's do it all over again for quadrant 3. Let's say you did a diagonal flip about the origin and your theta ended up over here. Okay, but you're not interested in theta, you're interested in this entire angle. Well, this entire angle, this is actually your theta reference, the 40 degrees, okay? Once it leaves quadrant 1, it becomes a reference angle, or principal value, sometimes it's called. So the way you would calculate this actual angle for quadrant 3 is you would add theta reference to the extent of quadrant 2. So you would add 40 degrees, because that's our example theta reference, plus 180 degrees to get 220 degrees, okay? And last but not least, let's go through the same concept in quadrant 4. So if you did a horizontal flip about the x-axis and your theta reference ended up over here. Oh my God, writing on this takes forever for me. I'm trying to speed it up. Okay, the way you would calculate this angle that you're actually interested in would be to subtract theta reference from the extent of quadrant 4, which is 360 degrees. So 360 degrees minus our example theta reference of 40 degrees is going to leave you with 320 degrees. Okay, so I think you get the point by now. All right, let's see. Is there anything else that we need to cover? Nope, let's get into our original intent. What is the range of the function y equals the inverse cosine of x, also referred to sometimes as the arc cosine of x? So these are two names for the same concept, the inverse function of cosine, okay? Definitely press pause. I'll give you a moment to think and draw out your answer in the form of a graph with correct, units labeled along the x-axis and y-axis. All right, so hopefully you've had enough time to come up with an answer, but if not, that's totally fine. The first thing that I want you to recall is that the range is a set of all possible values of the dependent variable where the graph exists, okay? And that's always going to depend on the independent input variables. So let's take a mini journey. Since the inverse cosine of x is the inverse of the function cosine of x, I want you to keep this in mind. The originating function y equals the cosine of x is not a one-to-one function, okay? And what I mean by that is that it's a function. A function can be determined by the vertical line test. So the cosine of x, and this, by the way, is a picture of the cosine of x function, y equals the cosine of x. It passes the vertical line test, meaning a vertical line slices it once along its entire domain. But it's not a one-to-one function, it's a one-to-many function, as I demonstrated by showing you that different angles in different quadrants can have the same cosine value. That means that if you conduct the horizontal line test, it's going to slice the cosine function at many different places. So the horizontal line test determines whether a legit function that has already passed the vertical line test is a one-to-one function. And we just established that the y equals cosine of x is a one-to-many function. That's why I showed you all the different, ways that you can have a reference angle in quadrant 1, but also have the same cosine value in other quadrants, okay? All right, this is problematic because if the originating function is not a one-to-one function, that means its domain becomes the range of the inverse function. That means that the inverse function won't be a legit function to begin with, okay? Because in order for a function to be a function, it has to pass that vertical line test. And you might not be able to rationalize this now in your head, but I'm going to show you, okay? All right, so what we're going to have to do is what I have already done here. We're going to have to restrict the domain of y equals cosine of x so that y equals the inverse cosine of x can become a legit function. We're not even thinking about one-to-one. And without restricting the domain, we're going to see that if we were to try to slice the inverse cosine function, it wouldn't be one-to-one, okay? I think I'm repeating myself now. Okay, so it would be a one-to-many function, and that's not what we want. A restriction can be done arbitrarily, but in the world of trigonometry, it's usually done between 0 and pi. Pi is 180 degrees, and although we don't have our pi is like a radian measure, although we don't have that labeled here, we indicate it in the x coordinate. You can think of every increment as pi over 3, okay? So it's usually taken between, the domain is usually restricted between 0 and pi for the cosine of x in order to yield a proper function or graph for the inverse cosine of x. So 0 to pi is the restriction region used for the inverse cosine of x, okay? And after restriction, the inverse cosine or the arc cosine of x can then be defined as the one angle between 0 and pi. Pi is 180 degrees, where the cosine is equivalent to this value of x, okay? And it is then a one-to-one function. And this is music to our ears. And you're going to notice that it leaves this restriction leaves the domain of the cosine of x range between -1 and 1. That's our answer, okay? I'm sorry I'm taking forever, but I just really want to make sure people really get this because it's very confusing for many people across the world, not even just the United States. Okay, so where do we want to go next? Yeah, so remember I told you earlier that the inverse cosine of x is the inverse function of y equals the cosine of x. And in order to generate any inverse function, you basically just switch the domain and range, or you switch all the x and y values. And the quickest way to do that is to flip the original function about the line y equals x. So this blue thing here is the line y equals x, okay? That's this diagonal line. That's what that represents. So after doing that, here goes our fabulous inverse cosine of x function. We see, I'm going to first, we want to know what the range is, but ranges are generated from domains, domain meaning all the independent variables. So we see that our domain is -1 to 1, and our range is from 0 to pi. So essentially all we did was we inverted or switched the domain and range of the y equals cosine of x to get the domain and range of y equals the inverse cosine of x. Okay? So some people need to know for their specific homework problem or class that along this entire restricted domain, the function is decreasing and it's inclusive. When I say inclusive, it includes the endpoints. Okay? Is there anything else that you need to know about this? Yeah, and so the beauty of this is that this function is a legit function. It passes the vertical line test. Let's say, for instance, that we didn't restrict it. What you would get is something that looks like this. Okay, and that obviously it doesn't pass. It looks like a dot money. It doesn't pass the vertical line test, therefore it wouldn't be a legit function. Things are getting a little messy. Oh yeah, and so like if you want radiant, I don't have it depicted here, but let's look at, I'm gonna take all this crap off for you because it gets a little confusing, and let's neaten things up a little bit, okay? Okay, yeah. So here we have a neat version of y equals the inverse cosine of x, and again we see that our range is from 0 radians to pi radians. Okay, and if you want to measure in degrees, you simply can change your vertical scale from you know, pi, whatever. You basically change from negative 90 degrees to 180 degrees by multiplying by the conversion factor, 180 degrees over pi. Okay, let me show you what I'm talking about. So this is a conversion factor for converting between radians and degrees. So 1 radian unit is equal to 180 degrees. Okay. Your the shape of the graph wouldn't change. It's just that degrees are way, like there's so many degrees, so it would be a really huge graph. That's why people just kind of condense it down to radians, because it's much, you know, more condensed. You don't want a big graph to take up all this space. The graph would be unchanged. It's just that there's so many units and things would get a little hectic. All right. So the range again is going to be from 0 to pi radians inclusive. When I say inclusive, including 0 and pi. That's why the circles are bolded in and they're not empty, okay? All right, this is like going on for too long. Hopefully you understand now. Thanks for tuning in.